Hi everyone, thank you for attending this talk. My name is Georgia and I'm a research scientist at FAIR. Today I will share some thoughts on reasoning about scenes and objects in 3D. The goal of visual recognition and the dream of every researcher working on this topic is to create a system that is able to recognize everything in a single image. The scene, the objects, the humans, their pose, their actions, and interactions with objects. For example, in this case, we want to be able to say that it's a street scene. There's 3 people clearly visible. Person A is walking away carrying 3 bags, while person B is looking at person C, and person C is playing an accordion sitting on a bench. The system should be able to localize all objects and predict the 3D shape. It should also recognize the scene and predict its layout. For example, person C is further away than person C, etc. The task is clearly challenging. Objects are occluded or not fully visible, there's a lot of clutter or noise in the scene that the system needs to ignore, and the objects have inter-class variation, which make it very hard to recognize. We have built systems that have taken us closer to this goal of recognizing and localizing things and stuff in a scene and parse their pose. This video shows the output of a panoptic segmentation system, MeasureCnn, and dense pose. But the examples showcased here make predictions in 2D. For 2D object recognition, the progress in the field has been tremendous. We have built models like MeasureCnn that localize all objects in a real-world scene under varying conditions of occlusion, clutter, number, and type of objects present in the scene. But recognizing objects in 3D is far more challenging. Here, we want models to predict 3D object shapes in addition to 2D object properties, once again having to overcome occlusion, clutter, and varying number of objects and types in the image. An effort in this direction, presented by Justin Jitendra and I at ICCV 2019, extends MeasureCnn to predict object shapes in the form of meshes. Our system, MeasureCnn, takes as input a single image. It recognizes and detects all objects in the image with 2D bounding boxes and instance masks. And it predicts the object's 3D shapes in the form of meshes in the camera view coordinates. To capture the varying topologies of object shapes, we predict intermediate 3D voxels, which are refined to produce the final mesh predictions. This allows the model to capture instance-specific object topologies with a more flexible representation, then converts it to meshes, which capture finer detail. An overview of MeasureCnn is shown in this figure. We build on MeasureCnn, shown here, that detects and recognizes all objects in the 2D plane. We add a voxel network which predicts the voxelized object shapes. Voxels are great because they can easily capture instance-specific shape topologies by merely turning occupancies on and off. However, they're bad at capturing fine details and are coarse. These coarse voxelized predictions are refined by our mesh refinement branch, which learns to deform the vertices with a sequence of graph convolutions. The final output is a refined mesh of each detected objects in view coordinates. MeasureCnn is able to detect and predict object shapes from real-world complex scenes end-to-end under viewpoint and appearance variations. But to extend a 2D recognition system to 3D, we need to deal with new data structures which are more complex than 2D image grids. 3D operators, which process 3D data. And of course, in order to train a neural network end-to-end, everything needs to be differentiable. 3D data is challenging, and even batching them is not straightforward, especially if the goal is efficiency. Batching 2D feature maps is trivial. You resize your 2D grids to have the same height and width and stack them in the first dimension. But how do we batch 3D meshes, which all consist of different number of vertices and faces? There is many possible batching modes for 3D data, including lists, packed tensors, or padded tensors. And what is important to note is that different operators work optimally under different batching modes. For example, in MeasureCnn, within the same forward pass, we switch between batching modes in order to maximize efficiency. 3D operators also need to be efficient and handle batch 3D data. In MeasureCnn, a big part of the network needs to operate on large batches of 3D voxels and meshes. An example is the chamfer loss, which computes the distance between the predicted mesh and the ground truth mesh. A naive PyTorch implementation of this loss operating on batch 3D data is too slow. Efficiency is key and is achieved by a custom implementation in CUDA. The same trends hold for other 3D operators as well. We packaged all these operators into a library of reusable 3D components that we call PyTorch 3D. This effort is led by our research engineer Gkioxari. Of course, apart from differentiable operators and efficient data structures, PyTorch 3D also includes a differentiable renderer for meshes, point clouds, and soon, volumes. Rendering is very common in graphics. You take a 3D scene composed of shapes, cameras, and textures, and render it to the image plane. However, traditionally, this process is not differentiable. Recent works have attempted at making it differentiable. Let's see how. Rendering is composed of two steps: rasterization, which computes which part of the scene affects each pixel in the image, and shading, which computes the color of each pixel. Shading is differentiable because it is just an interpolation of vertex colors or projections of face colors onto the image plane. But rasterization is not, because of boundary and occlusion issues. Let's see why. Consider the pixel shown in green. If we move the blue face from left to right, then the primitive that hits that pixel changes from the orange to the blue back to the orange triangle, creating a step function that is not friendly for differentiation. Similarly, if we move the blue face from near to far, the orange triangle comes in front of it. To alleviate these hard changes in the rasterizer, triangles are given smooth boundaries and blended. This was an innovation introduced by Sofres at ICV 2019. PyTorch 3D innovates compared to Sofres in three major ways. First, each pixel depends on its k-nearest faces instead of all. This makes the implementation efficient and enables modularity. Second, our rasterizer is implemented in a course-defined manner, which improves efficiency. Finally, shading is moved to PyTorch, which allows users to customize their implementation according to their needs. Note that this is unlike Sofres, where both rasterization and shading is implemented in a monolithic CUDA kernel and is thus hard to change and customize. In PyTorch 3D, the heavy lifting done during rasterization is done in CUDA. Shading and blending are moved to PyTorch. The overall renderer in PyTorch 3D flows as follows. Cameras defined by the user transform the object to view coordinates. This is done in pure PyTorch and admits gradients through AutoGrad. The rasterizer implemented in CUDA produces 4 outputs, which are then consumed by the shader and blending functions. Shaders support PyTorch implementations and thus admit gradients via AutoGrad, making it easy for users to implement their own. Here's an example of how one would implement silhouette rendering from the outputs of our rasterizer with 2 lines of PyTorch code. Here, this is the output of the rasterizer. And sigma is a hyperparameter that controls the blur of the silhouette and the edges of the shape. Of course, now we have to prove that our rendering engine works. We will showcase this for the task of 3D shape prediction from a single image, using our differentiable renders and no 3D shape supervision. However, there is shape ambiguity when learning to predict shapes from a single image. Infinite 3D shapes can explain the same 2D image. For example, consider the input image on the left. There is infinite shapes that can explain that image, 2 of which are shown on the second and third column. To overcome this ambiguity, we assume a 2-view training setup. At train time, our model, given an input image, predicts the shape of the object in view coordinates. It renders its silhouette using differentiable rendering, which is then compared to the ground truth. The shape is then transformed with a known rotation and translation to the second view, which is then rendered again and compared to its corresponding ground truth silhouette. This model uses only 2D supervision. It assumed object silhouettes for silhouette-based rendering, or the original textured views for texture-based rendering. And of course it assumes that the model has access to 2 views of the same object at train time. At test time, the network is able to predict the object's shapes and view coordinates from a single image. We conduct experiments on the ShapeNet dataset and the R2-N2 benchmark, which consists of 13 categories and hundreds of thousands of images. This dataset is synthetic, and images are clean, with objects in their center with no occlusion or clutter. It is far from the complex scene we see in the real world. However, it allows us to benchmark and compute metrics, and thus quantitatively compare to previous state-of-the-art approaches such as soft RAS. For the image encoder, we use a ResNet 50 network. For the shape network, we experiment with various architectures inspired by recent advances in supervised prediction. First, we try a popular model for shape prediction, which uses a sequence of fully connected layers to predict the offsets for each vertex, which are then used to deform a sphere template. We call this model Sphere FC. Inspired by MeasureCnn, we also experiment with a more geometry-aware architecture. This model makes a 3D shape part of the network architecture by allowing it to pull features from the backbone based on its geometry and perform geometry-specific computations via graph convolutions. This results again in offset predictions for each vertex of a sphere. We call this model Sphere GCN. We compare to the previous state-of-the-art in differentiable rendering, soft RAS. We replicate their experimental setup, which uses a Sphere FC model, deforms a small sphere of 642 vertices and 1280 faces, and renders at a 64x64 image resolution. We say that PyTorch 3D performs better than soft RAS. However, absolute performance is not good enough. The more geometry-aware Sphere GCN model performs much better under the same setting. To push performance even further, we deviate from the soft RAS setting and render at higher resolutions. We notice that both Sphere FC and Sphere GCN improve with higher rendering resolution, showing that resolution is important when using renderers, even for a simple dataset like ShapeNet. This emphasizes the need for rendering pipelines to gracefully scale to high resolutions, and PyTorch 3D does. From these experiments, we observe that PyTorch 3D works great. We also note that Sphere GCN, inspired by MeasureCnn, is a superior model for the task. This is also shown qualitatively. Consider these input images at test time. Sphere FC is able to capture the global pose and semantics of the input images, but it cannot capture specific shape details to accurately reconstruct the objects. Sphere GCN makes more accurate predictions, and note that both models learn to deform the same sphere. This validates the use of geometry-aware network architectures. So far, we've been sticking to a small sphere template of a few hundred vertices and faces, following the experimental setting of soft RAS. Thanks to PyTorch 3D and its skill efficiency, we can go bigger than that without much slowdowns in training or inference. We train a Sphere GCN variant that deforms a larger sphere. We call this variant high-res Sphere GCN. Now this shape has more degrees of freedom to try to simulate the shape topology, and our model does that while maintaining a good computational throughput. The predictions from high-res Sphere GCN look much more accurate in capturing shape details. Putting everything into a single bar plot, we note that PyTorch 3D skill efficiency allows us to improve the initial soft RAS baseline by a huge amount. To emphasize the good performance from our unsupervised models, we also compare to the state-of-the-art supervised MeasureCnn, shown in pink. We note that the margin between supervised and unsupervised has reduced significantly. PyTorch 3D also offers support for texturing meshes. We can easily extend our models to predict RGB values for each vertex, which learn to predict the shape's texture from the input image. PyTorch 3D's modularity allows us to play with various shading functions, lighting, and other aspects of texturing, all with pure PyTorch code. I will skip these results, but you can learn more about this in our codebase. We can also train unsupervised point cloud models using PyTorch 3D's point cloud renderer. We adapt Sphere GCN and train a model that starts from a sphere point cloud. Graph convolutions are replaced by linear layers applied to per point features sampled from the backbone feature map. We call this model point align. Point-align performs great for shape reconstruction and further reduces the gap with supervised learning approaches. This is also shown in our visualizations when reconstructing shape and texture. 3D is not only a property of objects, it's also a property of scenes. A scene changes as the viewpoint changes in a manner consistent to its 3D structure and layout. Objects in the back move faster than objects in the front. Objects become unoccluded or occluded when the viewpoint changes, and so forth. This is clearly shown in this video from New York Times. It is natural for the human eye to perceive the changes in a scene as the viewpoint changes. But how do we teach machines to do this? The task of novel view synthesis stress tests exactly that, namely whether machines can reason about the 3D structure of the world by creating novel views consistent with viewpoint changes. And here, the problem is related to both geometry and semantics. We use the ideas behind differentiable rendering for the task of novel view synthesis, an effort that was led by our collaborator Olivia Wiles and published at CVPR 2020. We're not the first ones to tackle this problem. A variety of methods have tried to synthesize novel views, focusing either on synthetic and single object images or using stereo and ground truth 3D supervision. Our approach uses a latent point cloud. A feature network encodes an image and produces per pixel features. A depth network predicts depth for each pixel. The 3D point cloud is transformed on the target viewpoint transform and rendered in the new view. The projected features are passed through a generator to produce a final image. While at train time, a discriminator makes sure the output looks natural. At train time, the target predicted image is compared to the ground truth. At train time, this method uses only image supervision, original and target view, and assumes a transformation between the two views. There is no explicit 3D supervision for this scene. We focus on complex scenes from Matterport, Replica, and Real Estate 10K, which all contain walkthroughs of indoor and outdoor scenes. Experiments show the effectiveness of our method, called SynSyn, compared to image-to-image approaches and methods that use latent voxels instead of point cloud representations. You can find more details on the performance and benchmarks in our paper. Here's some visualizations of novel views at test time. Even though we don't supervise our network with any 3D information, nor do we force it to learn an accurate point cloud representation of the scene, the model is able to make reasonable point cloud predictions. More interestingly, we show zero-shot generalization to novel higher fidelity datasets and to higher image resolutions without retraining our model. Finally, I want to finish this talk with a couple remarks and thoughts. Looking closer at our 3D predictions, we note that models fail in a very consistent manner, both in 2D and 3D. This suggests that the tasks are correlated, and improving one could improve the other. Finally, a question worth answering is whether we can learn better models and better representations by reasoning in 3D. SynSyn showed that a latent 3D representation was crucial for the task of novel view synthesis. Could this be the case for other tasks as well? And on that note, thank you very much for listening.
I've now been just fielding questions, and the first question, with all work that's gone on implicit representations, have you thought about implicit variants of MeasureCnn?
I was actually sure I would get this question. I don't know why. Yeah, I mean, I think that implicit functions are a very exciting new way to bypass all the issues that come with having an explicit representation, which is mostly resolution and compute. I'm actually, I am very sure that we will see more of these new trends and methods be integrated with models that we've built. A MeasureCnn extension to do with implicit functions, either that being SDF or anything else. I think is something that I believe we will see more of. I'm currently not working on it, but hopefully somebody out there is.
So can you comment on the differences between the differentiable renderer you use here and those that have become popular with approaches like NUF?
Yeah, right. So, so one thing to make sure that we need to disentangle is that differentiable rendering and all these methods that we presented here and methods like Krishna that you've worked on and other people are actually rather complementary to implicit representation. So in order to render implicit representations, you actually need to extract information from them. In NERF, rays are shot and information is accumulated along the ray. So you actually need to sample points along these rays in order to render back. So actually point cloud renderers can be used even with implicit functions with an intermediate step of sampling points, which is also what happens in NERF. So these approaches are not orthogonal at all. They're actually complementary. Implicit functions offer a way of how you represent the 3D world, the 3D scene, but rendering assumes that you need to sample explicit points on that scene in order to render back. So I wanted to make that clear that it's not two different ways. They're actually very much entangled.
Thanks. I now see a bunch of very similar questions, so I'll just put them together. Yeah. What are your thoughts on getting differentiable renderers to work on real images? Most papers using the rasterizers seem to show results in simulation.
Well, I think that this is a matter of, I don't think there is any reason why we're not doing it on real images. Like we have the technology, of course, compute and memory time. These are all things that we're still trying to improve in order to use them in real images. For example, in Synsin, where we used real images and we used differentiable rendering, we were not able to go into crazy resolutions of like 3,000 cross 3,000 pixels, let's say. This will be prohibitive in terms of compute. So this is definitely an axis and angle that we need to improve in order to make this work. But I think it's mostly about people being interested in doing the work in real images rather than synthetic data. So I guess my job here is to urge you to work on real pixels.
That brings us right to the next question, like 3D seems to have a dataset problem. Do you agree? And what are potential mitigation strategies to move away from ShapeNet if it makes sense?
Yeah, like I agree. Data has been a problem throughout computer vision, I would say. 20 years ago, if you asked a computer vision researcher, they would say, oh, we have no data. And so now it's like, this isn't a problem that will stick with us. 3D definitely suffers more. ShapeNet has been the testbed for a lot of experiments. We need to move away from it. We haven't found a good replacement. I do believe that simulated environments like Matterport 3, like Habitat, so environments that offer you the ability where you have a 3D scene and you can actually extract images, could be a very nice replacement that we could work on even today. Still, we don't have the variety and the number that ShapeNet has, but it's definitely getting there with more people adding scans to the data sets.
Good. So I'm going to take one last question. And have you used these models for different kinds of downstream tasks like segmentation or object detection, and how they'll perform relative to methods that don't use differentiable rendering?
Great question. Yes, we actually have, and this is sort of the kind of work that I am personally interested in, trying to see how we can use these ideas and methods for traditional tasks, for object recognition, in 2D, but also in other dimensions like time or 3D as well. They actually work very well. So it's not a method. It's harder to get into. It's hard to understand. It's hard to set up than a lot of the models that we are currently working on. But there is very much hope that we can use them and build on top of them to do even more, which is a limitation of current ways that we are doing 2D object recognition, which is very tied to the fact that it's 2D, but it doesn't have to be.
Thanks so much. So I guess in the interest of time, those are all the questions we could accommodate. But yeah, if there's any questions, please feel free to post them on Rocket Chat. And then, Georgia, whenever you have time, feel free to respond. And yeah, again, thanks so much for the talk. And it's great to have you at the workshop.
Thank you for having me and inviting me. And good job so far organizing this workshop.
Thanks.